In match problem 1, we're given a few different functions, and for each one we want to find the intervals for which that function is concave up or concave down. So what we're going to do is start off by finding the second derivative of each function, identify any critical values, and then construct a sign chart for the second derivative. So given negative e to the negative x, here we have a composite function. So the derivative of this is going to be negative e to the negative x times the derivative of negative x. Derivative of negative x will just be negative 1. So we get e to the negative x. The second derivative of our function then is the derivative of e to the negative x. So this will become e to the negative x. And again, we have a composite function here. So we'll multiply that times the derivative of negative x, which will give us negative e to the negative x. So there is no case where negative e to the negative x can be equal to 0. So we have no critical values to consider. So when we construct a sign chart for the second derivative of x, we can just choose any point in its domain and plug that into the second derivative. So in this case, we'll get negative e to the 0 power or negative 1. So for all values of x, our second derivative is negative, meaning that our function is concave down on negative infinity to infinity. And then we could sketch very roughly a curve of this function, and then you could plug that into a calculator to verify what the actual curve looks like. But eventually we're going to have a shape that looks more or less like this. So this exponential curve that's concave down. In part B, we want to do the same thing for the natural log of 1 over x. So here we have a composite function, but if we keep in mind properties for logs, we can actually rewrite this a little bit and avoid having to use the chain rule. So the natural log of 1 over x is the same thing as the natural log of x to the negative first power. Then properties of logs allow us to bring that exponent down as a factor in front, rewriting this as the negative of the log of x, or the opposite of the natural log of x. So to find the first derivative, that's just going to be negative 1 over x, which we could rewrite as negative x to the negative 1 to make finding the second derivative a little bit easier. So this will be positive x to the negative 2, or 1 over x squared. So 1 over x squared can never be 0 because there are no variables in the numerator, but what we do need to check for is anywhere where the denominator can equal 0, which in this case would be at 0. So our second derivative is going to be undefined at 0. And again, keeping in mind that this is a natural log function, this is actually going to be undefined for any values less than 0, so we don't need to worry about any negative values. We only need to consider a single test point here. So we evaluate the second derivative at 1, which is going to give us 1. And we see that our second derivative is positive for all values of x in the domain of the original function, meaning our function is concave up on 0 to infinity. And again, just sketching a really rough curve for this function, we're going to end up with something that looks generally like this. So we've got a logarithmic curve that's concave up. We could find some more information. We could find what that x-intercept is. We could find some points along the way to get a better idea, but that's enough to understand what the shape of that graph is going to look like. And then for part C, we have x to the 1/3. So our first derivative will be 1/3 x to the negative 2/3. And then our second derivative will give us negative 2/9 x to the negative 5/3, which we could rewrite as negative 2 over 9x to the 5/3, to again realize that this function can never equal 0, but will be undefined whenever the denominator is equal to 0, so whenever x equals 0. So in this case, at x equals 0, our second derivative is undefined. So we can choose 2 test points and evaluate the second derivative at negative 1, which will give us 2/9, which is positive, and evaluate the second derivative at 1, which will give us negative 2/9, which is negative. So our given function will be concave up on negative infinity to 0 and concave down on 0 to positive infinity. And then again, sketching roughly what this graph would look like. Even though our second derivative is undefined at 0, the original function is defined there, so we'll include that. We'll have a continuous curve. We'll have a curve that starts off concave up, and then at x equals 0, changes to concave down. Again, we could be a little more thorough with finding points along the way to understand where these curves are going to be in relation to the different quadrants, but we can get that general shape of concavity just from reading things off the sign chart here.